Moss for accepting our offer or requirement to give us a webinar. We're looking forward to it, and I'm going to hand over to you now.
All right, Peter, thank you very much. I appreciate that that introduction, and also I'd like to thank both of you and Alonda and Gary's help in organizing this event this morning. Appreciate you attendees online staying on here this afternoon. What I'm going to talk about here today, as soon as I share my screen, what I wanted to talk about today was some principles of basic well design, mostly acquired from experience, but also with some discussion of what's the latest technology that we have learned from other educators and that you can now research yourselves in several new textbooks. So what I'm trying to do is improve the overall thought process in water well design, going from strictly, let's produce a structure that's supposed to produce water at a certain rate, and let's give it a few more caveats. Let's put a few more expectations on our wells, and that's to say we want them to produce with the least amount of drawdown, the least amount of head loss, and the least amount of overall cost to the owner and operator. So I'll jump in at this point and run through slides here. So some of our topics here. We'll talk about the definition of well efficiency, and we'll discuss well losses. Then we'll talk about minimizing well losses with proper well design techniques. And some of these techniques involve gravel packs and the slot size selection process. So these deliberately affect the screen design, the intake design of the well. Now, I do understand in some of the areas where maybe some of the practitioners on this call work, the boreholes you construct may or may not include a well screen and an annular gravel pack. So what this talk will talk about is when those instances do occur. If you're in an alluvial type setting where you're trying to draw water from a sedimentary structure, this talk will really be based on the proper application of those types of techniques. Then we'll talk about some of the basics of the effective well development procedures, and a little bit more information at the conclusion of this talk, talking about new insights as to the intake structure itself. What have we learned lately about the design and application of well screens? I see a lot of people are still waiting to be admitted. So we talk about some of the basics of well dynamics, and this should be, fairly easily to come in concept here. We have a non-pumping condition. You have what's known as a static or non-pumping water level. You turn that well on or that borehole on, and what you're reading in that well with your measured tape, your wetted tape, or a transducer, you're measuring that distance from the static level to the total drawdown. That drawdown we can now understand consists of different components. And we look at the aquifer loss component and a well loss component. Those two, when combined, give us the total drawdown in the well. So we're learning that the aquifer loss is strictly tied to the hydrogeologic parameters of the aquifer, the texture makeup of the aquifer itself, the prevailing head on that aquifer, and this gives it the hydraulic properties that, when stressed, will give us the aquifer loss component, the number of meters that contribute to the overall drawdown of the well. And these we can't control. This is what Mother Nature says. You stress the aquifer as we understand, and this is the amount of loss that you will receive. These additional well losses, these several meters of additional well loss, for example, will be added to the total drawdown of the well because of things like improper development of the well or improper gravel pack size. So what I'd like to say is there's some basic categories we can look at in terms of improving the overall design. that you want to properly select that gravel gradation. Secondly, you want to select the proper slot size for your well. The improper slot size will also combine to give you additional head loss if it's too small, for example. One of the biggest contributors to head loss in a gravel envelope well is inadequate development. Often this step can be seen as something that's optional, or it's not completely understood, or not completely understood when to determine when development is done. So we'll take a look at that here in this program this morning and talk about what the overall goals of well development is and how you can actually take the proper steps to make sure it is complete. But if you leave, for example, residual drilling fluid in that borehole, and then you add a gravel envelope and you don't completely remove the effects of that drilling fluid, it is going to impede the entrance of water into your completed well. And this last point, where science is showing us now, is that there are also head losses that have to be accounted for actually inside the well itself. I'll have to admit, as a practitioner of well designs now for over 30 years, we've always tried to limit the losses, looking on what we can do or what we can control outside the well. But very little has been done to look at what's going on inside the well. Once the water enters the screen and moves upwards towards the pump intake, what kind of losses should be accounted for there. We'll talk about that at the end of the program too. So in figures here, I'll show you that what we were looking at is, say, a drawdown in the local aquifer here would be represented by perhaps this part of the yellow line. So that's our near well loss. This is the aquifer loss component. The additional losses can be imagined by these further drops in the line here. So the decrease in head here, first head loss in this damage zone. This damage zone, again, this would be residual drilling fluid per se, or inadequate development of the zone left this fine grain matrix, this bentonite material or hole stabilizers that we used during the drilling process that were fine as long as you were trying to maintain the hole stability during the drilling process. But now that the well's been gravel packed, screen has been installed, this now becomes an impediment to letting the water come through in a laminar fashion through the gravel pack and into our screen. There are further losses as the water moves through the gravel pack, as you can imagine. A relatively little or a small amount of the head loss is contributed as it goes through the well screen openings. And then I've added this last one because, again, recent research has shown that there is significant amount of contribution to head loss in the upflow. So that is, as the water enters the well screen and transitions from a horizontal to a vertical flow, this will account for a significant amount of head loss also. So we'll talk about these individually. And walking through the next series of slides, we'll talk about what we do during the design process. All right, we're talking about proper gravel envelope or gravel pack. I'll use those terms intermittently here, and then we'll talk about proper techniques of well screen opening design, and then we'll talk about some of the basic well development techniques. All of these, when applied properly, will reduce the amount of well losses you can expect in your well. And everything starts, in my opinion, with the actual borehole drilling process itself. So this is an example of a fluid circulatory system-based drilling process. So you're using a drilling medium to help lubricate the drilling bit as it's progressing downward. And it's also helping to lift the drill cuttings up and out of that borehole and then off to a settling tank, as shown in this case here. As a geologist, many of us have been out on sites and we're trying to characterize these sediments as they're coming up out of the hole. So we want to look at these cuttings and we want to look at the samples, looking at the texture, seeing if they're, igneous, are they metamorphic, are they going to be sedimentary? Basically just trying to glean some evidence to see if they have the capability of transmitting water, or are these from a water-bearing zone or perhaps a compact formation that's not going to give us much water. But whenever there's a change in the drilling tubing, that you can temporarily stop the drilling the circulation system, and now you can get a first-hand sample of the interval that the drill bit just passed. So for every 3 meters per se, or 6 meters of penetration, you can then get a sum total of the materials that it just passed through. So this gives you your first idea of what kind of materials that you're drilling in. Next, you're going to collect these samples at regular intervals, again, maybe at 3 to 6 meter intervals, and then you're going to examine them at the surface. And again, here, these geologists and engineers are looking at, okay, what zones do I want to perhaps conduct a sieve analysis on next? The sieve analysis is, we'll talk about that. That's going to help us determine what the gradation of this gravel envelope will be. So, but in addition to selecting the samples just based on a textural observation, we also can run geophysical logs. And this is just a quick example of one of the logs that you may run, say, down that open borehole before you run the casing and screen. This is an example or a portion of a resistivity log. And basically what you're looking at with these lines here, and many of you are probably familiar with these, is the relative resistance of a current to pass through the formations, through the drilling fluid and into the formations. So simply put, higher resistance is red as you progress to the right. And more resistive formations, for example, like this section shown here, and this is in feet, between 300 and say 375 feet. The higher resistance zones are associated with loose material. So if there's sands and gravels that you've seen in your physical samples coming out, you may start to say, well, this formation is more likely to contain water, as opposed to other type zones that have deflections to the left or have a lower degree of resistivity. These are very tightly packed formations, suggestive of tight grain-to-grain contact situations. So these would be more indicative, say, of silts and clays, and less likely to contain water. So the benefit of combining the real-time samples coming out of the hole with logs like these is that these resistivity logs can tell us where the tops and bottoms of the water-bearing zones are, and this will help us refine where our screening placement goes in our final design. And if we go through the selection process of those samples where we say, okay, this is where I believe I want my samples to, I'll run the samples closest to the zones where I think my screens are going to be placed. The samples are dried. They are then sieved. Nope. Sorry. Then they are run through the series of sieves where the coarse materials are collected near the top of the series of sieves and the fines collected at the bottom. Each of those samples are then weighed and then plotted on a format such as this. Now, some folks like to do percent passing on the y-axis and some will do percent retained. In this particular example, we're looking at the percentage passing each of these screen sizes shown on top. And for this example, we're looking at the US screen sieve sizes here. So basically, we're increasing from left to right in both the grain size diameters and in our screen sizes, this shown here. So we're looking at the gradations of, say, a sampling of some of the formation samples here. So this would be the finest portions of those samples, the mid-size, and then the coarser sections are here, mid-size, and the fine fraction would be down here. So silts and clays would plot down usually low and to the left. In selecting a gravel envelope, we're looking at the overall grain size gradation of the samples themselves, but then textbooks would tell you either pick the D50 or the D30. The diameter of the grain size is passing at 50%, or the grain size of the diameter is passing at 30%. And I'll use for this example the D30, and from there I'll choose a multiplier. Again, textbooks will say 4 to 6. You know, if you use the Benison book or even the Roscoe Moss handbook, those will say 4 to 6 times multiplier, say of the D30. But my opinion, we can push that multiplier out to a 6x9 because of improved well development techniques. We feel like we can adequately pull out many of the fines associated with the aquifers now that we can be a little bit more aggressive with our multiplier, yet still have an efficient well without producing sand. So if I use a multiplier of my D30 to 6 to 9, I'll end up from this 0.01 inches to 0.06 to 0.09. I have here a series of gravel packs whose D30 corresponds to that multiplied point, that 0.06 to 0.09. And they're pointed here. There'll be a couple of 4x16s and one 4x20, for example. So these would be on paper my first cut at taking a look at where my gravel pack gradation, what it should look like. Now that's not the only one, but we'll at least start at that point. Understanding that I need to choose a multiplier on this gravel pack that's not supposed to replicate what's there in the formation in textural grain size, but it's supposed to be many times larger. Some examples of the qualities you are looking for in the gravel pack. You want high silica content, number one. Why? Because silica is very stable.
Kevin,
yes.
Kevin, sorry, it's Peter here. Sorry to interrupt you. It appears if you've got your presentation over on top of another open box or something. Can you just confirm?
I'm trying to. I have this message that says move this window away from the shared application. It's constantly saying people want to be admitted. I don't know if I'm controlling the.
Yeah, no,
I have to admit those people in or not.
No, I admit the people in. We just. I don't know if that box can be removed. But anyway, it's not a big hassle. Let's carry on.
But you're seeing the same box that says remove this window?
Yes, everybody's seeing that.
Okay. I don't see the little X to remove it.
Oh, sorry, Kevin. Can you hear me? Maybe if you can just change your view and see if you can get that off so that it's not on top of that application.
Okay. All right, Yolanda, I'll see if
just see, because we have some comments that it is distracting. So let us try to just solve it so it can actually not appear. So maybe if we change your view.
Okay. So stop sharing for now.
Okay, perfect. Let us see.
Okay. Let me get the view back. Okay, I have it gone now.
Okay, on this side as well. Let us see how it goes. Thank you. Sorry for that, Kevin.
Thank you.
Sure.
I apologize for that too.
Sure.
Okay, so basically what we've done here, let me go. I was discussing some of the qualities of the filter packs we were looking for, but a high silica content is very, very important because we know this is a very stable element. So for the same reason that it's the most common element on the Earth's crust is the same reason why we'd like to have it in our filter pack. It's very stable. It is going to stand up through very aggressive development procedures, and it will be long lasting and even stand up to, say, rigorous redevelopment techniques in the future. So if you're going to use low pH solutions, for example, or acids in your future rehab development exercises, this high silica content material will remain stable and not break down over time. And again, it's important to maintain that properties of this filter pack, because if it breaks down, it will actually change its curve. And if you change that curve by removing certain elements of what you try to incorporate in its original gradation, now it doesn't behave like a filter anymore. It's not going to stop the fine materials from the aquifer from continuously to come in. So if you use a less noble material, materials that tend to break down fairly easily, it's not going to behave the way you wanted when it was initially put in. So we go from the gravel pack gradation selection process here to our screen slot size selection. So what I've shown you here is I'm going to select this red gravel envelope gradation here, and that's associated with something called 4x16. Now for the slot size I'm going to choose from my screen, I don't need to retain all of this 4x16. In other words, I don't have to retain such a tight slot size that I'm trying to retain all of this material. I actually can open up the window a little bit to allow 10 to 20% actually pass through, hypothetically. And again, this is the class book way to do it. Some textbooks will say pass no more than 10%. Some will say you can take that up to 20, depending on your familiarity with the gravel you're using and the development techniques that you like to employ. But if I pick a balance between the two, between the 10 and 20% passing, say I select a 15% passing using this filter pack. Well, if I drop down, I see this is a 0.07 mark. So this will be my 070 slot size. So I'll use 70,000ths of an inch in this example here. So that in a nutshell, I know it's been a little fast, but how I go from gradation of a formation to selection of the filter pack to now selection of the slot size. If you think about this progression, these progression of steps to get to this point, again, this is how you build proper efficiency, as opposed to sometimes too quick to jump to perhaps from looking at a particular formation, jumping to the conclusion, I need a very small slot size because of the relative texture of the formation, without thinking of, I have the ability with my gravel pack selection process to increase that slot size to its maximum size possible, yet still retain the sand retention properties I'm looking for. And just as an example, this is what you'd be looking at. On the far right would be representative of a very uniform fine grain formation. This would be a water bearing zone. This is, somebody's not muted. And this here would be a represented gravel pack whose, if you want to think of it this way, the lowest third in diameter of this gravel pack is 6 to 9 times larger than the lowest third of this formation, right? And the slot size here is selected, and it's about a 2 millimeter slot size is there, and it's supposed to retain 80% of this material here. So that's how we basically go from the formation to an aquifer to a gravel pack selection size to a slot size. Another type of filter that we've seen used or become more popular now is glass beads. I don't know if this has been an option that anyone on the call has looked at, but we've seen it here in municipal water well construction. We've seen it in observation wells, monitoring wells, and dewatering wells for some mining applications. And basically here, what you have to understand when you utilize a product like this, and now it's very good because obviously it's almost pure silica glass. There are some additives, but it's over 90% pure silica. They're perfectly round. So all properties are very good as far as transmitting water and being long lasting and stable. One of the detriments is to a filter pack like this is that it's uniform in size. You're not going to get a fine, medium, and coarse blending of beads when you utilize this. So you have to be cautious as to what kind of aquifer formations you want to use this product with. So for example, and you remember that previous slide, that formation was relatively uniform. We have seen occasions where that very fine sand will run right through the regular spaced interstitial, spaces between the beads and make it through the screen. An aquifer like this, or formation like this, where you have fine, medium, and some of these coarse grains, as I'm showing here by my cursor, if you have an aquifer whose texture includes these, then these will be very suitable to line up with the beads, because what I believe happens is you actually do some sorting. You winnow out the fines close to this interface here between the beads and the aquifer, so you build up your filter zone right out here. You take out the fines, you leave a coarsening layer right at this interface here, and now you have a nice clean transition from your aquifer to the slots. And that's some of the advantage of the beads. Some will also add that if you're in a zone where you have a lot of bacterial problems that tends to clog up your screen openings, and your local gravel pack, the bacteria won't adhere to these glass beads as readily as they would a natural filter pack, because the outer surface of the beads are so smooth, they just don't have a place to grasp onto. And then when you hit them with an agent, a dispersant, or an acid, they'll easily slough off. Final word about slot size. Again, what I try to employ people to think is, don't look at the slot size as the last hope for controlling sand. That's not the job. That's not the job of the screen slot. It's there to stabilize the filter pack you've just put in. But also understand that it provides the best opportunity for getting energy out of the screen, into that grout pack, into the local aquifer during initial development when the well is new, but also down the road when you go to redevelop the well. Again, it's your only opportunity to get significant amount of energy, product material that you might use to break down the scale if filled up in bacteria. The only way to get that material treated, broken down, and brought in and bring that in is through larger slots. Different types of screens, quick review here. These are 4 common types that you may become accustomed with, at least in terms of steel type screens. So the top right, I'll go clockwise. Top left is our shutter screen or louvered screen. Top left is, then we move to our right. This is the wire wrap screen or wedge wire screen. We have a bridge slot screen here, and we have slotted screen. Roscoe Moss Company has at one time or another been associated with all of these different types of screens. So we know a little bit more about the proper application and maybe, misapplication of these in some cases. Right now we are manufacturing actually the top 2 shown here, the louvered screen and the wire wrap screen. We do have our pipes slotted when it's required. We are no longer producing bridge slot pipe. We understand it is still commonly used in Mexico and some of the Central American countries. I'd like to start providing some information here about screen comparison studies, both in the field and in laboratories, that will help you as you move forward. If you're looking at a particular screen design, what are the important components that you need to understand to a well screen, beyond just simply looking at the perceived benefit of open area alone. So in some of these examples here, we'll look at field examples first. So these are some field comparison studies. 3 agencies here were selected where they had different open areas of their screens. And then we also looked at the performance that resulted from these 2 different screen designs. Our first example would be from Los Angeles Department of Water and Power. They had 2 450 millimeter diameter wells. These went down to about 500 feet or in depth. Specific capacities were very close. 0.8 here to 0.8 liters per second per meter, and overall efficiencies of 85 and 78. The differences between the 2 are very slight in their performance, if at all. Yet, if you look at the percent open area in each of the screens, we were 5% here and up to 38% here. So we're starting to, this is one of the first studies we looked at, was like, what could be the cause of the relative similarity in the performance despite the large difference in the open area of the screen? Next one was Orange County Water District, where I was once employed, and we had another study we did comparing 2 well designs. These were both 300 millimeter wells with a specific capacity of 2.7 on the 5% open area screen and 2.2 on the 30% open area screen. Again, relatively very close, despite the large difference in the open area of the 2 screen types. The last one is the town of Wendover, Nevada. Now here, there were 2 different diameters used. A 300 millimeter test well that was producing a specific capacity of 4 liters per second per meter and an overall efficiency of 75. When a 16-inch production well was constructed nearby, right, same design as the test well, but this was the full production well, It was a 400 millimeter diameter well with the 38% open area screen, but it did not outperform the 300 millimeter well, nor was it as efficient. So this even brings more questions to mind and tells us that why didn't open area improve the production in this instance? They were done by the same contractor, done to the same depth, the same screen zones were selected for each of these two wells. It starts to indicate that there are other factors that contribute to the performance of the well and the overall efficiency of the well, besides just looking at a single factor, which is the open area component. Then we started looking at historic papers, studies that had been done. And you go back to the early 80s, and you'll find a few. Again, this is just a few that are more commonly found. And this one was written by Clark and Turner in 1983, and they tested several screens in the laboratory experiment, and they said between the range of 5 to 40% open area they tested, there was really no advantage of above a 10% open area screen. But what they did subscribe to is that good development techniques and progressive development will improve the overall efficiency of the well. I'm sorry, we're down to that darn window again. Let me see if I can go back and come back in. There. And another study that was done in 1984, we look at a research study that included both field and laboratory studies. And in this case, they tested well screens where they found over a broad range of open areas, 6 to 38%, that the 6% open area screen performed as well as those screens which had an open area as high as 38%. They also looked at the sand migration issue and to see if it was controlled by slot size and entrance velocity. And they found that was not as true as they once thought, that the sand movement was actually influenced by the discharge rate, the hydraulic gradient that develops at a certain rate and in a certain part of the screen, and the velocity in the formation near the well. And finally, they concluded here that the entrance velocity should not be limited to 1/10 of a foot per second or 0.003 meters, and should not be a design criteria. And again, many of us subscribe to this thought process today. As those of us who are hydrogeologists on the staff, we like to think, at least I'd like to think, this is geologically controlled. Our entrance velocity is a result of what the hydrodynamic properties of the aquifer are, combined with the stresses applied by the pump. That a given screen cannot determine what the entrance velocity is by itself. You need to complete the structure and then conclude with the pump tests, and then determine what the incremental velocities are over the overall screened intervals, not just an average. Another study that was done here in 1985 was performed by Dr. Dennis Williams, a well-known scientist here in the Southern California and Southwest area of the US. He tested 6 screens with areas ranging from 1 to 36%. And his conclusions from his studies show that over 90% efficiency can be achieved with screens with as little as 3 to 5% open area. So this corresponds very well to the field studies I spoke early on, both in California and then Nevada study, that 3 to 5% open is what you need to get a minimum of 90%. And also in terms of entrance velocity, velocities as high as 2 to 4 feet per second will produce overall efficiencies of 90%. This is why, say, a national standard that we look at now for American Waterworks Association, we've selected a value of 1.5 feet per second. And that is our national standard that we commonly apply here. But if you're interested in this article, this was also published in the American Waterworks Association in 1985. And that's available for your review. Some of the modern textbooks that we can now look to. This is one here produced by American Society of Civil Engineers. It was published in 2014. The reason why I like this book is that it took some of the contributing factors to what I initially showed you in head loss. Head losses through the damage zone, filter pack, the well screen, the well bore, and then actually inside the well casing itself. These authors identified those particular components, but then went further to actually provide mathematical formulas whereby you could determine the contributing head loss components for each one of those individual levels. So one example would be calculating head loss in the well screen. So without going through all of those, but if this is their formula that they derived for calculating the head loss just through the well screen itself. And so you can see the parameters on the left that are included in this formula. And some of them are constants and some of the variables. Obviously the Q is going to be a variable, percent open area, radius, overall screen length. We have a constants here with this coefficient of contraction. And then lastly, what's nice about this formula, they look at the performance of the screen in terms of how it's actually operating underground. And especially if you're looking at a gravel envelope well, you know there's material that is right up against that screen slot opening, that it should not be measured or evaluated as if it just came out of the factory where every slot is 100% open. So they've given this clogging factor presence in this here. So what we'll look at then is, for an example, if your screen diameter was 400 millimeters, the length of the screen was 30 meters, discharge rate of 63 liters per second, and let's say a constant of your coefficient of contraction was 0.61, and a clogging factor of 50%. You calculate the head loss using that 5% open area value in our previous studies. We'll say the overall drawdown just from the screen itself at these production levels is less than a millimeter. It's going to be 0.4 millimeters. You redo the formula with 18%, and it only contributes to 0.05 millimeters. So overall, very, very small contribution to the overall head loss, the overall drawdown on the well, just from the screen itself. So this tells us as long as we develop that screen properly, more open area is not going to necessarily give us higher efficiencies or any more or any less head loss. This is another new book that comes out and answers the same issues. Now this one takes a little more look inside the well and what's going on during its operational time. So with Mestier, Banks, and Clark, in their book, they discussed the study that they were involved in. This was in Bangladesh, where they looked at 17 different wells with different screen types. That included the wire wrap, a mesh wrapped slotted plastic, and slotted fiberglass wells. And the screen lengths ranged anywhere from 18 to 36 meters. And the diameters of the wells measured anywhere from 100 to 250 millimeters. And what they determined was that the theoretical losses that they calculated agreed very well with the actual well losses derived from pumping tests. So what they did was then they took an average of all the theoretical contributions from these tests. And if you look at where they're attributing most of the head loss to, screen upflow losses, shown here, 63%. Losses above the screen, in other words, in that zone from the top of the screen interval up to the pump intake, they attribute 34% of the head loss to. So between these two alone, your 97% of the head loss in the well occurs after the water has already entered the screen, according to these authors. And then if you look outside the screen, what's going on in that near well gravel pack and the entrance actually through the screen slot, it's just slightly over 4%. So the conclusion of these studies are looking at where should our losses be, where should our focus go in terms of looking at losses? And does the simple application of a high open area answer our need for high efficiency? And then lastly, this study here shows this was a high-powered computer model that was run by a company called Amphos. We at Roscoe Moss were trying to research some of these head loss components through the screen, and further we're going to take this study to learn more about the dynamics going on inside the screen and the well itself. What kind of head losses are being introduced based on screen type and screen geometry? As a manufacturer, this is important for us to know, because if we can make modifications to the way we provide these screens to certain users, we can help reduce overall head losses. So in looking at a 5%, say, louvered screen, and that's what this simulation shows here on the left, versus a 25 to 30% open area wire wrap screen here, this is what the study showed. If you can imagine your mind, talk about the louvered screen here, this is the steel, this is the white area here, that's our louvered screen here. These are the slot openings. So here's the water moving from right to left, coming into the screen barrel at a speed of 0.018 meters per second. Similar flow rate, 0.16 meters per second through a wire wrap screen, and you can see each of the different contributions of the water coming in through the different wire profiles here. You can see based on the velocity scale here that you've got a higher velocity through the screen openings, even though these openings are the same size, in the wedge wire screen. You also have a higher level of turbulence inside the screen than you do in a similar louvered screen based on these entrance velocities. This is telling. This tells, well, why would that happen? So we start looking at, well, what is it with the geometry? Is it the upflow? Is it transition going from a horizontal to vertical that's causing this? This very well could be, and this deserves more research. As opposed to over here, okay, as the water comes in, is there an advantage to the already oriented flow moving upwards towards a pump intake, for example? The transition from a horizontal to vertical is less severe here. It's already joining the flow in a tangential manner. And perhaps this produces less head loss because of the entrance direction. Something we're going to be looking at more. So now we move into the well development section. And you can look at development of your well in 3 different periods of the well life. When it's brand new, when you're constructing the well, controlling the drilling fluid properties is certainly something you and your contractor can observe, control, and stay within certain limits to make sure that that drilling fluid is doing its job in terms of stabilizing the hole, but also can be sufficiently removed during the initial development process. The preliminary development process, swabbing, jetting, flushing with fresh water, airlifting and bailing sediments off the bottom, takes place after the casing has been set and your gravel envelope has been in place. And then your final development, again, this is not always done, but is highly urged, is to put in a test pump. And this pump should have the capability to pump at 150%, let's say, of the value of the final pumping rate. And the reason why you want to do that is perhaps you want to stress the well and the aquifer to make sure that you have a full understanding of what the aquifer's capabilities are, but also you're going to use this as a development tool. Most of the tools, as I'll show you, are great at developing the near well zone, certainly the gravel pack, but if you can incorporate a large test pump at the end, now you're incorporating some of the near aquifer areas and starting to remove some of the fines from the local aquifer itself. So this is what we think when we're trying to accomplish during the development process, that we're going to repair the drilling damage. That term means I want to break down this wall cake or this residual drilling fluid that's left in the borehole after the well's been drilled and the gravel pack set. So this is the aquifer material. I want that to be clean. I want my filter pack clean, but I want this wall cake broken down and removed. One tool that we found to be very effective is this dual swab tool. And basically what it is 2 rubber swabs or belt type of rubber swabs snugly fit, cut to a diameter that's no smaller than a 1/4 inch smaller than the ID of the casing that you're going down, separated by about 3 meters of pipe that is perforated. In this manner, when this goes down to a brand new well, and is located, and you can place this on a piece of an end of drill pipe or drop pipe, you can flush fresh water out or dispersing chemicals out to break down the clays and silts. And it helps consolidate the filter pack while also flushing with fresh water through this type of zone. So this type of tool is best used when it's reciprocated up and down over, say, 1 to 2 meter, 3 meter intervals. So that way you're backwashing both on the downstroke, and then on the uppull, you're pulling that material back in. And the secondary application of the same tool is to incorporate an airlift system now. So now the swab tool, as it reciprocates up and down within the screen, isn't just moving the same dirty water in and out, but this acts like a vacuum. So you can stop the tool at a certain level of the screen after swabbing for a certain period, and then activate the pumping system. And now this is going to withdraw all the fine material that you've just loosened up and get it out of the well once and for all. This is also a very good application when you're redeveloping wells too. So after the well is 5, 10, 15 years old, hopefully no longer than that, this type of tool can be used, again, going down with chemicals, acids, dispersants to help break up any scale or bacterial buildup that may be on your screen intakes that also would probably be proliferating out in your gravel pack as well. Very good for that purpose. And for overall evaluation of your well development, there's 2 parameters that you can look at. This one just looks at specific capacity over time and sand content over time. So in a new well example, we know if we look at the sand content shown here, it's going to start out very high, maybe around 200 parts per million. But over time, over a series of several hours, now we've got days here in this example, but for deep wells, say 300 meters or more, this may be the type of development time you're looking at. So your sand content would start out high and it would fall, decrease, and then it's going to probably plateau at a certain amount. If you wanted to shoot for, as a rule of thumb, some commonly accepted value for sand content, it should be less than 5 parts per million. All right. Our other parameter that we measure over time during development is specific capacity. In this case, it's just gallons per minute per foot, but you can do liters per second per meter. We can look at that value. That's going to start out very low on a newly constructed well. Why? Because of things like that wall cake that were shown in previous photos. The well is not developed yet, so we're not pulling that water in the most laminar manner possible. There's still a lot of turbulence caused by the residual impacts from the drilling that we need to remove. But over time, that value will improve to eventually it'll plateau and you'll reach a maximum specific capacity. So when 2 things are achieved, your maximum specific capacity and your minimum sand content, this can kind of be the scorecard to tell you when development is complete. And these kind of relationships can also be used not just when the well is new, but if you're going into a redevelopment effort or rehabilitation effort, utilize these same kinds of analysis. So this is how we think our well is done. All right, so when we're all said and done, we've developed it properly, we've applied the right filter pack gradation techniques, we've cleaned the aquifer out significantly or sufficiently during our development process, our well screen is clear, the slot size is properly selected and open after you develop it, well, that's fine. But what happens a few years down the road, you know, Mother Nature kind of takes over here, and now we start seeing more well losses creep in. So despite our best efforts during the design and construction process to build efficiency into our well, now we have to maintain that efficiency by watching how the well performs over its lifetime. Because things like scaling happen. You could have mineralization clogging those screen intake areas. You can have physical clogging. Fine sand can clog very fine slots on some screens, and this blinds it. This is going to cause further head loss in the well. This right here, this is bacterial buildup. This will also be a large contributor to head loss because it's going to clog your screens and also be proliferating in the gravel pack zone itself too. So what will you see as an owner operator? You're going to be realizing these well losses, right? They're just going to happen. All right. So what you're going to do is you're going to see through you know, if you're taking regular drawdown measurements and taking regular discharge measurements, you're going to be watching that specific capacity value. And likely if it falls over time, it's going to start giving you symptoms that you're losing efficiency. And you can also check your electrical costs and see if your electrical costs are going up, because now you're having to lift the same water in the same amount over a higher lift. So these are some of the symptoms you'll see if you allow the intake structures to be impacted by issues such as these: mineralization, sand clogging, and bacteria. So I've got just some points to close with overall, and I think it really starts with, you know, beginning with the understanding of the hydrogeological character of the aquifers itself. I know from being a well owner, well designer, and now where I stand in my position as a manufacturer here, but you know, the well design starts best when we really understand what the hydrogeological character is and what the aquifer is capable of delivering. The best you can do in a design that you apply and your best construction practices, the best you can achieve is is to get the most out of the aquifer. You're not going to get more than the aquifer is capable of delivering and still be efficient. You want to consider the grain size distribution, understand what that grain size distribution is, what water quality parameters are, what the depth you're going to, and your length of service life of these wells. All of these go into the types of materials you purchase, whether you're going to use a stainless steel, for example, because you have corrosive conditions. Understanding these up front can also determine to what type of steel you want to use to make sure it meets your length of service life. Now we can understand a little bit more what contributes to well loss. We need to account for those up front. So when you're designing the well, and then as you operate and maintain this well, make sure you understand that there are well losses that are going to occur after the well is done, and you need to keep up with regular maintenance on that. And think long-term and not just only short-term when you think about designing boreholes. It can be enticing to look at, say, always the low cost or the least expensive options, but sometimes those become the most expensive ones when we look down the road, because perhaps, you know, decisions were made to not use a corrosion-resistant steel or not use a heavier wall material. But now we realize due to rehab conditions, boy, that structure is not very sound now, and I can't get as aggressive as I want to in my rehab program. So make sure you think long-term and think of what maintenance may be required, and make sure I think about my design process up front. Take that in mind. Again, in terms of geology, do not prioritize hypothetical screen production values over aquifer production. Again, it's tempting to say to derive values based on the hypothetical, either entrance velocity or production value, what a particular screen type can do. Sure, that can be an exercise, but what actually is far more important is understanding what the aquifer production value is, and let that determine what your overall well should produce. And don't prescribe an entrance velocity. Again, that value is derived after the well has been completed, and is completely the function of the way you operate it, the way you pump it, the amount of screen length you put in, and how well you maintain the well. Trying to put on a limit on the design process may lead you down a path towards unexpected consequences, because it may lead to an improper gravel pack, an improper slot size, and actually increase your head loss. So again, utilize your analysis of your geological materials that you have at hand, and use the proper gravel pack and slot size selection techniques. And in thinking about screen slot sizes, don't consider the decreasing the slot, and don't consider the slot as a sand control measure. That's not what it's there for, and it actually won't control sand. Let the gravel pack, when you're using an inner pack, let the gravel pack determine what it needs to be, and let it hold back the fines from the formation from coming into your well. And then if you're not the well owner, but if you're a consultant and you, it's your regular, function to provide well design services to your clients, try to incorporate a long-term maintenance program for them where somebody is monitoring the well specific capacity, the pumping rates, the drawdowns in the well, and keeping those records, and then looking at the data, plotting long-term results to see if action needs to be taken in terms of redeveloping and rehabilitating the well. And in that manner, you're increasing the efficiency, at least maintaining the efficiency of this well. I think I'm, right up against my time here. So if Peter, if there's time, or if anybody has any particular questions, I can let you, Peter, let me know if there's anybody queuing up for questions.
Yeah, thank you very much, Kevin. You spot on with timing. That was really it reminded me again of the effort that one needs to put in when you planning the gravel pack and the well design. Thank you very much for that. I think if there's any questions, if anybody wants to ask a question, please let's allow 1 to 2 minutes. I don't know if anybody would like to type in the chat box any questions. Let's allow 1 or 2 minutes for that. And in the meantime, while everybody thinks about questions, I would just like to thank Yolanda from the Groundwater Division, allowing us to use their Zoom platform, and then from the Groundwater Association of KZN. Thank you for all the participants and for our Exco team putting this together. And then, Kevin, I think that was an excellent talk, and I don't see any questions popping up in the chat box. Let's see. So let's give it another 30 seconds. But anybody would like to? Okay, here's one. How does topography influence the well design? I don't.
Well, I suppose, there's a couple of things. I mean, some of the logical ones would come to be, what kind of apparatus are you going to mobilize based on the topography? Can you get a drill rig based on what the current topography looks like, and to make sure if you're going to have a 300 meter well, for example, just make sure that you can get a drill rig to a site. It's accessible to a site with very difficult topography, but overall, you just simply have to look at where are your water bearing zones most likely to be found. I can't say I think there isn't any particular topographic challenge I can identify at the top of my head, but I think it more leads to, where do you really think your water bearing zones are? Make sure you have access to drill down to them first.
Yeah, maybe one last question from Neville. Is there a certain minimum amount of time recommended for well development when using the test pump and straining the well? And is the point of maximum efficiency easy to distinguish between reaching a recharge boundary?
Okay. Yeah, a couple of points in there. Each well is going to have its own probably unique response to the development period, and that's why we give it some parameters that you can actually measure in the field: the sand content and the specific capacity. So again, each well is going to have its own capability of reaching the minimum sand content and specific capacity. But I would say, and it's also going to depend how much total screen is in the well. You should look at, just as again, rule of thumb, it's going to differ from space to space, but if you have if you want to have some sort of a guideline, if you were an hour on every 10 meters of screen, that would be considered a development interval for a piece of screen. That might be easier to understand than say how long to develop the full well. But if you take an incremental value like that, I think that's probably a fair way to assess how much time needs to be allotted to developing a well, for example. The second part of the question was the point of maximum efficiency easily distinguished between reaching a recharge boundary. Not quite sure about that one. Usually when you're, from these, I usually apply this to a municipal type well, a production well, where you're probably not too concerned about reaching the condition of a recharge boundary. In other words, you would have understood this in your well siting assessment, saying I would have understood the parameters of if I have a fault, I have a impermeable boundary or something like that. I think you would take that into account, number one, when you site the well. Secondly, I think if you dig into some of these textbooks and some of these applications where they give you these formulas, you probably can draw out what is really a well function versus an aquifer function. So I think you can, but I probably don't have time to go through all of the detailed explanation just based on the time left on the call.
Yeah, no, there's 3 more questions, and I think let's
Okay.
keep to those 3. We don't have much more time. The first one is boreal clogging is a challenge in many parts of South Africa. Do you think there is a preferable well design to reduce or eliminate clogging? Or do you think monitoring is the best solution?
Yes, I understood. I am somewhat familiar with some of the challenges there in South Africa, and certainly supplies, materials, and then again I do talk about the gravel pack and the importance of that and the qualities of that, and I do understand there's certain challenges just having quarries nearby, that have exactly what I was talking about, a nice more rounded and high quartz content materials. Again, those just can't be found everywhere, so certainly that is a challenge. But as far as a well designed to reduce or eliminate clogging, I think it goes back to taking a harder look at the gravel gradations for your gravel packs. If you're doing gravel pack wells, certainly see what your options are. Look at deposits that are probably being used for maybe other industries, for example, and saying, can I look at materials being used not just for construction industries, but for other services that give me the roundness factor maybe I'm looking for. That will help. Round grains against any intake screen are preferable than flat lenticular grains because they'll tend to lie right in the slot itself and therefore blind it. So rounded materials, for example, better than flat and lenticular as an example. And then that slot size component, use the largest reasonable slot size you can. Again, I know this is difficult because some folks get very, very concerned about sand content coming into the well and figure I need a tight slot size to control that. But actually it's a balance, and it does take a little bit of experience and a little bit of trial and effort to learn the right gravel gradation coupled with the right slot size. And that will reduce your clogging potential.
Okay, the second last question. Within Central Africa, especially in the highly weathered area, Roscoe Moss screens are usually recommended as the best screens, but mainly Johnson screen seems to be readily available. Any reason for that?
Well, I guess we have more to do there, but no, but we do, we ship our products all over the world, and it's certainly not difficult to get materials there. Our Roscoe Moss Company actually operates a plant in Egypt, and we're certainly able to service the African continent from that facility. And we also, in addition to that facility, out of the Los Angeles office where I'm located, we regularly ship materials to ports all over the globe. So if there's something you need from us, without sounding like a commercial, you have my contact information. Please contact myself or send it through info@roscoemoss.com, and we will have the proper people get a hold of you and make sure we answer your questions and get you the materials you need. But it's not a challenge for us to get materials to that part of the country.
Thank you. And then the last question, could the positioning of the pump in the well be used to limit vertical flow losses? And does the length of the screen affect vertical flow losses?
Yes, this is an issue that has been brought up before. It's not new, but we've looked at it. We've read a lot of data on this, and some folks will subscribe to, okay, there is a paper out there, the author escapes me right now, but if you move the pump to the intake part of the screen, you would decrease the head loss in that screen compartment. Remember, several of the authors I talked about recently pointed to attributing a major portion of the head loss to frictional losses and so forth inside the well itself. So that's true. Positioning of the pump can help reduce that, but at the cost or at the risk of inducing higher entrance velocity those near the intake screen. So if your screen, say like a wedge wire screen, and you're having high velocities coming through there, there's not much metal there to protect against the high amount of flow of sand that may be incorporated with that would just abrade that screen material, and now you open up the slot, and now you've got a bigger sanding problem. So I know hypothetically placement of the pump can sound advantageous, but in a practical sense, you have to ensure that it's not going to cause a sanding situation within the well intake. So that really attributes to how hard are you pumping, what pumping rate are you going to use, what gravel pack did you use, and what is the nature of the fine grain material that may be in the aquifer that's going to act like sandpaper coming into the well if you over pump at those zones. So that's the danger of putting a pump in the screen. And as far as the second part, does the length of the screen affect vertical flow losses? It's been believed that this will help. The longer the screen interval, obviously you can divide, again, it's going to change from well to well, but you can divide your contributing error over a longer interval and help get more water coming in from different zones. So it's just not all prioritized at one area of the screen. There you get higher entrance velocities and perhaps a sanding issue. So if you can provide more screen to your water bearing zones, probably the better off you are.
Yeah, no, I think the rest of the comments there is just to say thank you to you.
Oh, well, thank you to you. Thanks for everybody sticking around. I know it's after 5 o'clock. It's probably beer time for you. And
yeah, it's early morning there. Thank you very much. And yeah, we will keep touch with you. Thank you very much, Kevin, and everybody that joining us, supporting us. Thank you very much. Have a great evening further.
All right, Peter, thank you so much. And thank you everyone who attended the webinar today. I certainly appreciate your time. You have my contact information. If you'd like to reach out directly, please do. Thank you again.
Thank you, guys. Okay, bye-bye, Kevin.
Okay, bye, everyone. Thank you, Peter.
Okay, bye-bye.